All right, good morning. Thanks for coming out after lobster and beer and everything like that. I really appreciate it. And I'm going to be opening up for a series of talks. And in usual fashion, I'm going to give you my take-home messages first. Oceanography has changed in my career. You know, I was trained as a classical biological oceanographer, extracting chlorophyll and acetone and all those things. Still do that. But we can do so much more now. And so the issues are about how do we design experiments with these new technologies, because it's a whole different way of thinking about it. And you'll have lots of examples. When I first got into the technology space, there was sort of a race to build platforms. And we're still building platforms, but what's nice now is platforms are getting pretty mature. And so, you know, when I got young faculty coming into my office, you know, what do you need? Well, we need the sensors that can fit on these new platforms. And that was not the case before when we first deployed the glider for the first time with Doug Webb. We had a rope tied to its tail, we had to do a profile, we pulled it back on the ship and declared victory and didn't touch it for a year. Now they're out there all the time and it's what is it measuring? The other thing is you tend to become a specialist in technology in your little sphere. So gliders, remuses, deep sea stuff. But now as we're building networks, it's really about sensor webs, about combining lots of different technologies to give you sort of a synoptic synthetic view. And so we need to think about that. And then I'm going to just give some perspectives of new directions. So here are the talks we're going to have. I'm sort of the blonde morning tapas, and then this will be your entree. You know, you're going to have Craig, who's going to talk about how you sort of combine many of these different platforms to go across the scales. We're going to have an example of the sail drone, which is completely cool. And then we're going to go into the mesopelagic. And so, again, to sort of drive home the theme of how much it's changed, in my professional career, here's what I've sort of seen. You know, it's like, well, I started with an interest in technology. My dad had a lab in the back of the house, and we would build, you know, all kinds of things. But sort of as I was in grad school is when you sort of had Stommel's bold vision and TOS sitting, you know, here in Woods Hole with the grad students up in one of the rooms, you know, racing gliders across ocean basins. I first got introduced through Ray Smith at Santa Barbara, where at that point, the autonomous systems weren't really, they were still maturing. It was more ROVs, so it was tethered systems and stuff. And so I got a flavor of it. And really then you had people like Jim Bellingham, Chris Van Alt, who was here at Woods Hole, essentially developing a whole new class of autonomous systems that now are just commercially available. They're used by industry, scientists, and everything like that. In the late 90s is when you started having these alternating experiments. There would be an East Coast experiment 1 year at Leo 15, and you'd have big networks. We would see what would work. And then the next summer, you had ASON out of Monterey Bay. How do you combine those technologies? How do you couple them to models? Argo starts getting deployed, and by late 2000s, the platforms are mature. This is Doug Webb after the glider got to Spain. And his motivation was really Henry Stommel, because they lived next door to each other and they would drink beer in the backyard. And the vision he laid out was their afternoon discussions. And so what was really nice was watching Doug get very emotional about finally realizing their backyard beer discussion. You know, and so one thing I think that we're ready to do as a community is there's been such a revolution of what we do, and it's really never been documented in terms of these big efforts in a synthetic view of those incremental steps of all these things. So I think it might be a good thing for us to do. Well, I got to do the usual, why do we need these autonomous systems? Well, humans have their limits at sea. So here we are on the back deck of the RV Gould on a beautiful Antarctic day, deploying moorings. Nice vertical line heading straight out. So what does that tell you? We have a safety line on. And of course, you send your grad students out there. You know, you send your grad students out because the paperwork of losing a graduate student is less than an undergraduate. You do not lose an undergraduate. So we can't sample things in our traditional ship way for all the processes we need to study. A good example from, you know, my neighborhood was Hurricane Sandy and Irene. We cannot sample that from a ship, obviously. And yet, while there's been great improvement in hurricane track trajectory, there's been no improvement in hurricane intensity at landfall in 30 years. Why? Because the ocean is the fuel can, and we don't sample the ocean during the storm. Now we have systems that can. The other thing is we need to maintain a presence at sea. We are always going to go to sea. We're going to do experiments. That's what we should use ships for. But what we also need to do is fill in the gaps when we're not there. So how are we going to do that? More wise, we got to sample space. If we think of sort of the theme of OCB, this is my favorite sort of CCCS image that Tom Dickey gave me. And so look at this nightmare. You know, and so let's say we want to do the carbon fluxes in this part of the ocean. We're going to have to resolve a lot of this heterogeneity in space and time. So how do we 4D sample, and how do we do it affordably? If you do a model simulation of how many moorings we need to put off the west coast of California just to figure out whether carbon is going into the ocean and out in the cross-shore mode, to do that for California, ROM's model simulation suggests you need something on the order of 18 moorings. And these are these big, expensive moorings, which would be beyond the scope of any one project to do. You know, it's OOI scale in terms of numbers. So how do we sample the space? And how do we do it cost effectively? You know, what are the technologies that are scalable? Because if it's not scalable, we can't deploy enough of them. So what you're seeing here is sort of cost, US dollars, days at sea. The dotted things are different class ships. So the green is like a coastal ship that a university might have for day trips. And the solid lines are essentially gliders being deployed, ranging from 1 to 6. And what you see is you quickly can recover your costs for an initial investment in technology. You know, when I showed this figure to Rick Spinrad, he first got very angry with me, because the one thing we have to keep emphasizing is technology is not going to replace humans going to sea. In fact, what we found is when we do big experiments, the need to go to sea actually increases as we have more information. We can ask better questions, and we know what experiments to do. But we need to be able to sample 4D space, and we need to do it cost effectively. So what's great is different technologies, and I'll just give a quick sort of superficial sort of sampling of them, are mature. And so you can be a small group. So, you know, I'm just a lab. I'm not an institute or an institution. And this is what we've been flying with gliders as of last night. So we have one right now heading to Sri Lanka in the Indian Ocean. And so as a group, you can have a global footprint. And while we've seen that you're going to lose things, we've lost 9 gliders over the since 2003. We've done, you know, 272 missions based on the criteria of this paper by Dan Rudnick, and our success rate's about 84%, with a loss rate of about 3%. What are the losses? In the very first year, 4 of the losses were we were still working at the handshaking with iridium. And because we work off the Mid-Atlantic Bight, and your glider happens to surface in one of the big shipping lanes with the container ship, I can tell you a glider will lose against a container ship. You know, most of the losses currently fall under 2 groups that we find. If you have a new experimental sensor, pressure testing of sensors, actually the manufacturers do a good job, but they could do better. And when they don't do a good job, you find out because it never comes back. The other one is animals. Biofouling, and I'll show an example of that, is still a fundamental issue, and it's been since we've been going to sea. So we have great opportunities there. The other is animals. So if you're a surfer in the West Coast, and you see a surfboard from below, it looks like a seal, right? And that's why you occasionally have a shark attack. A glider with its wings going up, an AUV, you will have shark attacks, and we've lost 2 gliders to sharks. But the main thing is over time, for our group anyway, we're running on average about 30 glider missions a year. And we're essentially spending, about 1,000 days at sea. Varies year to year versus projects. And we're covering, 15 to 20,000 kilometers underwater every year. And so labs can be at sea 365 days a year. And that is something that was not what I was trained in, but it's awesome because the best part about being an oceanographer is going to sea. And now you can do it while you teach. You can pretend to be involved in your committee meetings, but in the background, you got other stuff on your screen. And we can be oceanographers all the time. And I find that really inspiring and fun. There are many different systems. I'm going to obviously be a little slanted to gliders just because that's my space. We were also working with Chris Van Alt for years in the early years with Remus. And the propeller systems, just like the buoyancy-driven systems, have made great progress. They're big, they're small, they all have different capabilities. You can go from the Gavia system here where they're just slopping out with, big boots and dropping into water to like really Ferrari systems like AutoSub. They can go under ice sheets and things like this. And so part of this space, when you're a young scientist and you get your startup package, you've got to think about what science questions and what spatial and temporal scales you really want to focus on. If you're going to really go after high resolution heterogeneity, you're probably going to want to go with the fast, smaller ones. And then if you need to be out there for sustained periods, you're going to go up to the more robust long-time systems. And what's great is these are commercially available. That wasn't the case before. So, you just whip out your Visa card and you do it. Actually, the funny story, Mark Moline is probably one of the guys, I think, pushing the edge with what you do with Remuses. So his first 2 Remuses, he actually called his American Express card, had him raise the limit, and then got all the paperwork for reimbursement ready, and essentially got all the miles for his travel that lasted his family for about 5 years based on his startup of Remuses. So be creative. And so when you're just sort of looking through the space of what you want to do, you sort of have to keep in mind what's the duration you want to be in, what's the horizontal distances you want to cover, and we cover a really nice space. The ones up here, they tend to be slow. So if you want to study animal behavior or something like that, these are probably not going to be the best ones. These tend to be much faster in terms of sort of how quickly you can map, but you can't be as sustained. So we've got a range of systems. We can be in the water all the time, and we can measure the ocean interior. And I'm not really emphasizing so much the deep stuff. Charlie Erickson and Craig are sort of pushing the envelope of deep buoyancy things. We got the deeper Argo, and Dana's going to give examples of more capable platforms for the mesopelagic. Surface vehicles. This is something that has been innovated, more recently. Wave gliders, essentially out there for very long, sustained periods of time, collecting data. This is data that was from the Gulf of Mexico during a big storm. Sail drone, you're going to hear examples of these kinds of technologies is in the Bering Strait. And these really are optimally designed to study fluxes at the interface. So if we have great carbon sensors and the associated measurements of the interior, these are probably going to be the platforms that are going to get you the interface and the interaction with the atmosphere. And again, depending on the model, they might go fast. They're going to have different ranges and durations, but you'll need to choose which one you want. Another one that's really accelerating are UAVs. And we're still getting a handle on it. And probably one of the things that's slowing down progress the most is the regulatory climate. You know, on the other hand, because there's a huge commercial interest in this, you know, all the kids want their own drone, the cost of this is really trivial compared to some of the other systems I just talked about. So this is Dave Johnson. He's got his little UAV down in the West Antarctic Peninsula. We go down there, we drop off, this is Adelaide Island, and we drop off 2 or 3 penguin people. They live in a tent, and they've got 5 days to count every single bird on the island. Dave Johnson puts his UAV up. It has many different sensors in its bay, and in 20 minutes, he gives you an RGB image, a thermal image, and a false color image. You can actually see the penguin colonies here, and there's about 10 to 20 centimeter resolution on these systems. And in the thermal image, they can actually count the penguins based on the thermal signature. And what's great is the thermal signature of a chick is different than an adult, so we can actually census how many chicks versus adults in 20 minutes. At least have the data. You know, the other thing is you know, essentially looking at animal behavior. This is a bubble net of 2 humpbacks. This humpback's coming up, and you can see the bubble net essentially forming. And so you can actually do lots of behaviors. But for OCB, what's relevant here is multispectral sensors in the visible spectrum are not prohibitively expensive. And so when we think of the optics that we want to use to constrain these carbon models, there's no reason we can't do a survey of a coastal site every single day, or 10 times a day, depending on what you want to do, and essentially look at those dynamics. Off the state of New Jersey, they essentially have a plane that they've been flying to do water quality every summer. It costs them $2 million. It's actually a waste of money. They don't know what to do with the data. You could replace it with essentially a $20,000 sensor and a grad student and a good computer. Yeah. So here's another space in terms of we can sample the lower atmosphere from chemistry in this. So we can do the interior, we can do the interface, and then we can do the atmosphere. But what are they measuring? You know, so I started just sort of doing a census. If we look at sort of a basic food web from an OCB sort of interest, well, we got physical issues in terms of transport mixing. We got trace gas exchange. A lot of the biology in terms of microbes right now, we focus on in situ optics, you know, and heat budgets, chemistry, zooplankton. And I've sort of listed all the different sensors I know of that are either commercially available or close to being commercially available. The greens are essentially those that have already been incorporated in autonomous systems. Then there's oranges, where there's groups that are that have them on some platforms, but not all autonomous systems. You know, and the reds are where we have great opportunity as a community to fill the gap. And what's actually really pleasing is we're starting to fill in a food web and essentially being able to take them out in autonomous systems to be able to maintain that sustained presence. Yeah. And so what we're finding is a lot of the faculty in groups we know, they're no longer writing proposals to buy a glider. They're writing a proposal just to build a science bay with their sensor in there. And then they've got that as a tool that they can essentially plug into the global network. And so, you know, I really think that we're in a position where we can make great progress in this. The early progress, we should really do a shout out to the Office of Naval Research, because they had some applied missions that really forced some of these technologies into the systems very early on. That investment is now being replaced by NOAA and NSF, generally from what I see, and we got a lot more we can do. I wanted to give sort of examples of some of the new technologies coming online. If you're an animal person, the active acoustics space which before we would say, oh, it's too much power. You're never going to do it. You can't transmit it back. That's changing. This is a plot from a 2012 paper from the British Antarctic Survey where they did very careful work of calibrating their active acoustics, and these are krill swarms where they could even see indications of where they thought that the krill were pregnant versus not. I'm skeptical, but the fact that we're having that discussion is actually really promising. This is a new sensor that's on Slocum gliders. This was measured by the University of South Florida, and you can see the vertical migration of zooplankton and fish simultaneously collected. And you can buy that bay now for a glider for just a measly $90,000. But if you think about it, if we have one of these science bays and we have coastal surveys going on, we could essentially measure the zooplankton communities every week for a shelf. And that's an amazing opportunity that we've never had the opportunity to do before. On some of the more powerful AUV propeller systems, this is an example of data from Bellingham, who's now at Hui, but this was when he was at Monterey. Here's a holographic image that he collected from one of his AUV systems. And you're starting to get snapshots sort of in that microzooplankton ranges. The sensor, the list hollow, and there's other ones out there, you know, essentially in the past have been very big, but there's already an effort to redesign them to fit on the range of platforms you can do. So you can go for small animals as well as big animals. Another area of opportunity is we have a lot of standard measurements that are out there. So here are backscatter pucks. This is called a BAM, used to be a SAM. It's looking at attenuation. But if you measure a bunch of these optical proxies and you develop a good algorithm, you can generate a new data product. And so the other thing is we have these autonomous networks out with lots of data streams, and if we make that data open to everybody, there's going to be a smarter graduate or undergraduate who's going to develop a data product we all need. So this is Mike Twardowski who developed this, and you're looking at essentially his estimate of how many of the particles had a mineral signature from a glider. Yeah, so having the students focus on using existing data streams to develop new useful data products is something we need because we have more data. We can start going after rates. So this is one of the fast fluorescence induction relaxation emission fluorometers. It's a Falco toy. Obviously here you're looking at essentially, you know, the quantum yield for photosynthesis measured on a glider. So here's your nighttime, there's your daytime fluorescent quenching. But if you know the quantum yield and you know the light flux coming in, you can now from a system essentially measure the equivalent of a photosynthesis irradiance curve autonomously. And if you know the light coming in, you can actually estimate the number of electrons the photosynthetic system is generating, which is photosynthesis. And we can essentially start thinking about rates. You know, how we do metabolic rates and everything, that's another question. But we have a big food web. We usually do them with boxes. We have these arrows we don't connect. How do we do that? And I think we can start making progress there. We can go for particle size. This is a brand new sensor. It's a list system, and so you're looking at a transect along the coast during a big winter storm, and you're getting essentially the beam C, the mean size of the sand particles at resuspension of the total volume. So particle size distribution is coming. Chemical sensors, there's an ongoing effort between Rutgers and Hui to essentially get the Durafets to get ocean pH in. That's going to be tested. So this whole space is accelerating in terms of making progress. The other things we got to do is make our robots smarter. A technician in a lab can handle about 8 gliders. If you give them 9 gliders, they rebel and then they blow up and die. And so you can make a lot of decision making on. So we're working with a group that's essentially got a supercomputer chip, but it's low power. So there's no reason in the future, if let's say you're under ice or this or that the glider could run its own ROMS model. We're getting at the point, and the decision is do you want to do that? Do you want to do that? But that's actually something we can do. You can also give it basic behavior. So here we've got a sort of behavior we built in where, okay, here's temperature for a glider, and have it essentially look for the gradient and hover around the thermocline. So find a feature and stay with it. So there's great possibilities there. And then we got to transition to thinking about how do we put all the systems together to solve lots of questions, and how do you move beyond just being a one-trick pony with one sensor on one platform. So here's an example from the Palmer Station in Antarctica. We're interested in what's the foraging dynamics in the Adelie penguins in a sort of topographically carved canyon here. We have climatologies of where they forage through radio tags on the animals. So you can see the climatologies here. So what we do is we set up broad surveys with gliders. They're slow, but they can maintain a continuous presence. And at the same time, we're getting real-time feeds of where the gliders are swimming versus where they're foraging, so you can calculate essentially a foraging kernel. And then that allows you then to just send in the REMIS with a shorter duration, but carrying a much larger instrument payload bay, looking at the physics, the circulation, the krill, the acoustics, to essentially then really define the hotspot. And so it's a 24-hour cycle of essentially this providing context to interpret their dynamics to essentially allow you to send in your high-powered Ferrari. And so it's usually experiments like this or several groups working together, and it's a very dynamic, adaptive culture where you're making decisions on the fly, but the tools are flexible enough to allow you to do it. At some point, we probably want to automate these things, and so we've been sort of playing a little bit with various groups on that, where we have ROMS models giving you very nice regional forecasts. The modelers are actually getting better and better. I'm an observationalist, so that's why I say that's like amazing. But if you have a forecast giving you a prediction of what's in the future, you can, in your model, embed hypothetical gliders or AUVs to see what are they going to be sampling in a future ocean. And then you're going to have those systems in the water. This was an experiment off the New Jersey coast. We had 4 gliders in. It's going to collect data that's going to be assimilated in to the model, and we're going to be able to, in real time, look at a salinity profile from a glider versus a model, and then essentially decide how much we trust the forecast. And the scientist lives in here. So this whole outer ring, the human is out of the loop. The human's here looking at the visualizations, but isn't creating them. That's fully automated. And so we wanted to follow the model of like the National Weather Service. The Weather Service runs many models, right? And they get a halo of what the sort of mean is between the models. They see if there's an outlier model, and that's actually really informative. So for this experiment, we had 2 different versions of ROMS running, 2 versions of the Harvard Ocean Prediction System, and one of the Princeton Ocean Modeling Prediction. And so we called them just Model A, B, C, D, because if you put the person's name by it and their model didn't look well, they got really pissy. So we're running a forecast mode of 4 models. We're getting a real-time feed. I believe the gliders are the green, the red is the model, and you can see how the model's doing in terms of temperature and salinity. And so for this particular run, Model D was doing pretty good in the temperature, pretty reasonably well in the salinity, and we said, okay, this is the model we trust. So then for the data assimilation part, we focused on Model D. So then we do the data assimilation, we run our forecast, and now we have a forecast of where the gliders are, and this time slider is a time slider going into the future, 2 to 3 days. And you can see where the gliders are. That's where the tail, the yellow the halo around them is where the glider can get to in the future. So if you slide, close to like time 0, it's a small halo, and then you can go 2 days out and you can see where they is. And so the scientists could essentially sit there and decide, well, one wants to sample a river plume, another one wants to look at a fish plume, whatever. And you can see where your glider is going to be in the future and make a decision that way. So we decided we want to send this glider to a river plume. So rather than have my technician sit up and do all the waypoints, we're going to hand it over to a model. to essentially make those decisions. So here's position reference, where the model controlled where the glider flew, and it's sort of, this is error. So the resolution of the models is this solid line. If you're below the line, the model's doing great. It's getting you where you want to go. If you're above the line, the glider's not where it's supposed to be. I see the raw data, I go, models suck. And then I actually look, no, the glider sucks. Compass failure, failure to update. So the model forecasts are getting resolved and accurate enough. If you trust it, in the future we could potentially use it as a flight tool to essentially plan our missions and hand over control. And then you can tie it to larger systems. So if you have a glider that's controlled by a model, you might want to have it control a satellite. So Hyperion is a tiltable swath, and we're essentially handing over control of Hyperion to this glider here, which is controlled by a ROMS model. And essentially the swath was supposed to be here, but the glider called into the NASA flight plan thing and shifted the swath over this glider. And again, the human was not in the loop. And the point I want to end on here is we don't want every lab to be building big networks, but the community now is coming through a lot of these national aggregation efforts. So if you go to AUVs, for example, you can go into the data assembly centers. Here are the glider missions that have been flown and that are in the data assembly system, and it's getting to be a much more comprehensive list of what gliders are out there. Here's the HF radar, here's the animal telemetry network. So if you're a single lab, you can run your one mission funded by whatever agency, but if you put it into these global aggregation networks, everybody can make a much larger statement for context. So I'm actually going to end there. I want to just say that the technology is becoming easier, it's becoming more robust, and it is becoming cheaper, and I think it's a really exciting time. So thank you very much.